Hello my students, your physics teacher Hassan Darwish with you. I'm going to record a series of videos about chapter 3, the angular momentum of a particle and of systems of particles. So let's start. Now the first objective, define angular momentum. Second objective, state and apply the theorem of angular momentum. Now third objective, identify the condition of conservation of angular momentum, and finally apply the law of conservation of angular momentum to solve problems. Okay. Now, what is angular momentum? What is the real definition of angular momentum? Let's consider a particle M moving in the xy plane along the trajectory C. I mean this trajectory. Okay? You know, for every particle moving, there is a linear momentum, right? And you remember P equal, here is a linear momentum, P equal what? Equal mv. You studied last chapter. But because v, which is the velocity, here instantaneous velocity, is always tangent to the trajectory, and m is a positive constant, so the linear momentum P of the particle is also tangent to the trajectory, right? Now r is a position vector of this particle m, here's m, position vector with respect to O. So the angular momentum of this particle m with respect to origin O, here is the origin O, is defined as sigma equal cross product between the vector r and the vector p. Okay? This is the most general definition of the angular momentum of a particle with respect to a point, or with respect to an axis passing through this point. Okay? So sigma, but you know that r is a vector and p is also a vector, and we have here a cross product. Usually in mathematics you write the cross product between two vectors something like this. So the sigma, which is the angular momentum, is also a vector, and this vector must be perpendicular to the plane containing r and p. But look here, the vector r exists in the xy plane, and also the vector p exists in the xy plane, and sigma perpendicular to r and to p. So sigma, here it is a vector perpendicular to the xy plane, right? So it is parallel to z-axis. So sigma is a vector parallel to the z-axis. Now what's the magnitude of this vector? In reality, we do not consider in this class this general definition of angular momentum. I mean any curvilinear or any curve in the plane. We will confine our study on circular trajectory. We confine our study on circular trajectory. So here is a trajectory, a circle, and I mean here, let me use another color. Say this is, for example, x, y plane. Here is x and here is y, horizontal plane here. XY is a horizontal plane, and the circle lies in this horizontal plane. Now Z, which is now referred to as delta, here is the z-axis perpendicular to this plane. So what's the angular momentum? Remember, it is a cross product between the position vector r and the linear momentum p, which is always equal what? mv, right? So if you do the cross product, then sigma equal rp sine 90. Why 90? Because p is perpendicular, tangent always to the trajectory, I mean tangent to the circle. And r is along the radius of the circle. And you know that the tangent and the radius of the circle are always perpendicular. There is a right angle. So rp sine 90. Sine 90 is 1. And p, here is p, equals what? mv. Remember this rule. So it becomes Rm. You remember from last year when we studied circular motion, or in this year when you made the revision, the angular speed theta prime is equal to V over R, radius of the circle, right? So V equal R times theta prime. Here is V is R theta prime. Now R times R squared. Then you get mr squared theta prime. But what is mr squared? We studied last year when in rotational motion that mr squared represent the moment of inertia of a particle with respect to delta, right? So I equal mr squared is a moment of inertia with respect to delta. So we conclude that sigma equal I theta prime. This is for a particle. Okay? So sigma mr squared theta prime. Mr squared for a particle is I. So sigma equal I theta prime. We can apply this rule directly. Okay? Now sigma is an algebraic quantity. I mean sigma could be positive number and negative number. If this particle m, as you see, moves in the previously chosen positive sense along the circle, here anti-clockwise or counterclockwise, then we say sigma is positive. But if particle m moves clockwise, clear, like this, and the particle and the positive sense is chosen anti-clockwise, then sigma is negative. Why is this? Because here we have cross product, okay? And this vector could be along the positive x-axis or along the negative x-axis, depends on the sense of p here in this case. Okay, let's solve an example quickly. Let's apply this rule. We have in this example the planet Neptune describes around the sun an approximately circular trajectory of radius 5 times 10 to the power 9 kilometer. The period around the sun is 165 years, means each revolution or each turn of Neptune around the sun is equal to 165 years on Earth. Okay? So if your age on Earth is 165 years, then your age on Neptune is 1 year if you live there. Being very far from the sun, Neptune is considered as a particle. Calculate sigma of the planet, I mean Neptune, with respect to delta, perpendicular to the trajectory through the center of the sun. Okay, let's start. Here is our Neptune. Clear? This is its linear momentum. P equals mv. okay, which is also always tangent to that trajectory. Here's a circle, and this is a position vector r. Okay, let me choose the positive sense like this, in the same motion of Neptune. This is delta, axis delta, passing through the center of the sun. You can say this is z-axis. You know that. Make the pen a little bit thicker. Sigma is what? Sigma equal I theta prime. Okay, let's first calculate I. I for a particle is mr squared. Now try to do the calculation to save time. If you do the calculation, then you get I equal 25 times 10 to the power 50. Now what's the unit of I? Kilogram meter squared. So kilogram meter squared. Okay, we need now theta prime. You remember theta prime equal V over R, right? But also you remember it is 2 pi over the period. Let's do the calculation for period in detail. This is 6.28 radian. 2 pi 6.28 because pi 3.14. Now the period is 165 years, right? 165 years. Change year into day. We mean 365 days each year. You can say 0.25. Now each day is 24 hours, so times 24 hours. Each hour is 60 minutes, right? And each minute is 60 seconds. Okay. If you do the whole calculation, you get 1.21 almost times 10 to the minus 9 radian per second. Okay, now replace I and sigma here. Replace I and theta prime. You get sigma approximately 3 times 10 to the power 42. Now what's the unit? Unit is kilogram, as we said, kilogram meter squared radian per second. So kilogram meter squared radian. You can write radian and you can ignore the radian per second. Okay, this is enough for this video. See you in the next video. Take care. Bye bye.